Okay, so let's start. Okay, so last class, which was module 3, okay, we talked about the counting rules. And what does the counting rule tell us? Anyone? What does it tell us? Anyone wants to try? What does the counting rule tell us? So we had 3, right? We had permutation, which was ordered subsets, permutation, combination, and also the multiplication rule. Why did we need these rules in the first place? Why is my handwriting extra ugly today? Okay, so why do we need these counting rules? Anyone? If you don't know why you need the counting rule, then you don't know when to use it, right? So why do we need it?
To deduce probability.
Again? To
deduce probability.
To deduce probability. Okay, that's one answer. So your friend said, let me remove. This is me, by the way, drinking coffee. So one answer said to deduce probability. That's a fair answer. Of course, to deduce probability. It helps you to get something to find probability. So what is that something? Yes, this is the bigger picture, correct. What do you find using the counting rule to deduce probability? It doesn't directly deduce the probability for you, right?
To know how many events have happened.
To know how many events happen. Or I would like to correct your statement, to know how many outcomes of that event. To know, it's a good answer, to know how many outcomes of that event. How many? Or we can say event. It applies to the situation. To know how many outcomes. I'm going to write it in general form, outcomes, okay? To know how many outcomes. Why do we need to know the outcomes? What is the outcome? Why do we need to know outcomes? Is it important? So someone said to deduce probability. How is probability related to outcome?
To know the possibility of something happen.
Sorry, I can't hear you again.
To know the possibility of an event occur.
To know the possibility of an event occurring. Okay, I'm gonna make your statement more accurate. To know the frequency or how often the outcome occurs. To know. So the counting rule. So the probability is related to how often an event or outcome occurs. How often an event outcome occurs. What else do we need to know the probability? So the counting rule helps us to know how many outcomes, which is how often it occurs. So what other thing do we need to know probability? This is not enough. This is just one parameter. So it's obviously not enough. I'm recording, right? Yes. What was the other thing that we needed? So if I write event, I have an event A, let's say. Event A is me recording the weights of my students in this statistics class. Okay, so I'm not going to reveal my weight. So let's say Saravana, sorry Saravana, I'm going to use your name. Saravana is 50 kilogram, for example. And how is 51 kilogram? And then who else? Faris Irfan is 55. I don't know, I'm just making this up. So for event A, we have 50, 51, 52, sorry. This is not event yet. This is your sample space. Because this is the I'm recording experiment. The experiment is weighing the students in the statistic class of Dr. Nadia Hussaini, right? So the sample space is 50, 51, 52. What was it? Irfan is 55. Faris Irfan. And who else? Sol is, I'm going to make Sol lighter, 45, etc., etc. Okay, so I'm recording all the weights of you guys. This is my sample space. This is the population, right? And then I want to say, let event A be that weight that is less than 50. It's going to be a little bit. Weights that is less than 50. Let event A be weights less than 50 kilogram, not milligram. Okay, so you guys are not particles. Okay, so let event A be weights that are less than 50 kilograms. So now my event A is 50. No, 50 is not less than 50 kilogram. Less, so I will only have one, 45. So it's just this guy. Sorry, it's just Sol, right? So A is 45. So this is my event. An event is a subset of the sample space. Your sample space is your population. Event is part of the sample space. In the sample space, this is your outcome. Okay? So that's just a little recap. Okay, so I'm gonna go over this again and again because obviously it's a new concept to us and I want everyone to really understand this. So again, what's the definition? The set of all possible outcomes of an experiment is called the sample space for the experiment. For example, I told you guys, I was recording the weight of my students. So the weight of you guys is my sample space and that is the outcome. So S is equal to blah, 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 okay? So this is my sample space. A subset of a sample space is called an event. So let's say I say weights greater than 50 is event B. Weights that is less than 50 kilogram is event A. So obviously, if you have a population of weights, right? And I just want the weights that are greater than 50 as my event, then this will obviously be a subset of the population. We know what subset is. Subset is only a chunk of the entire population, only like a small part of the population, not the entire population. Okay, here we have an example. An electrical engineer, such as myself, okay, I used to be, has on hand 2 boxes of resistors with 4 resistors in each box. Okay, so we have 2 boxes. Each box has 4. The resistors in the first box is labeled 10 ohms, but in fact, the resistance are 9, 10, 11, and 12. And again, I told you before, sometimes we declare a certain number for the item, but in reality, the value is not exact, just like batteries, right? So the resistor in the second box is labeled 20 ohms. Sorry for the mistake in spelling, but in fact, their resistance are 18, 19, and 20, and 21. Okay, so this is the first box, and this is the second box. The engineer chooses one resistor from each box and determines the resistance of each. So the engineer chooses from one box and determines the resistance of each. So what is my outcomes for this experiment? Anyone wants to try? At least one of the outcome from this experiment. Okay, so here I'm going to write sample space. What would be my outcome? Anyone wants to try? Just give me one. One resistor from each box. What would be my outcome?
9 ohm and 18 ohm.
9?
9 ohm and 18 ohm.
9 ohm and 18 ohm, okay? 9, sorry. That bracket should not be there. Great. 9 ohm and 18 ohm. That's your first one. Okay, let me just bracket it because you have a lot. Okay, next. Who else wants to try? It's correct. Thank you.
10,
10,
10 and 19.
10 and 19, correct? More. Come on, guys. Keep it coming.
11 and 21.
11 and 21. Okay, more. Anyone else? We have 60 here. 60 people here. So I'm expecting more answers. Okay, come on, come on. What is it? It's easy. Come on. What is the outcome for this sample space? Okay, I'm going to put the number myself. 9, 18, 10, 19, 11, 21. I want to put 9, 9, 19. That could also be a possibility, right? 9, 19, 9, 20, 9, 21, 10, 19, 10, 18. Okay, so let me write that down, or should I? Okay, let me just write it down first. Okay, let me try my best to write this nicely. Sample space. So we have 9, 9, 18, 9, 19. Okay, and 9, 20, and 9, 21. So I'm doing this in this order because I don't want to miss any pairs. Why is it a pair? Because the engineer is taking 2 from each box. So it has to be a pair. That's the possibility. Can it be 9, 9? Is it possible for the engineer to choose 9, 9?
No.
No, because we need to take 1 from each box. So if it's 9, 9, then the engineer is taking just from 1 box. And that's not our experiment. Okay, so 9, 21, 10, 10, 18, sorry, 10, 18, 10, 19, you get the idea. 10, 20, 10, 21, etc. Okay, up until 12, 21. So you have to list out all the outcomes if they ask you for the sample space. Okay, let A be the event that the first resistor has a resistance greater than 10. Greater than 10. And let B be the event that the second resistor has a resistance less than 19. Is it a chat? Okay, no. If you have questions, you can ask me directly, or you can type it in the chat box if you're too shy. And then let C be the event that the sum of the resistance is equal to 28. So this is a lot. So let's do that. So let event A, let me write that. I'm supposed to do this. Okay, so what is event A? Can someone tell me? The first resistor has resistance greater than 10. Which one is that?
11 and 12.
11 and 12. So all the pairs that has 11 and 12 will be event A. So 11, 18, 11, oops. Need more space. Let me, how do I do this time? Okay, so event A, I'm gonna write that down. Okay, so 11 and 12 for the first resistor, right? So all the pairs with the first resistor being 11 or 12 is within the event A. So 11, this is not helping me. Okay, 18. 11, 18, 11, 19, 11, 20, 11, 21. Okay, so this is not yet done. 12, 18, 12, oops, 12, 19, 12, 20, and also 12, 21. Okay, if you have any questions, you can ask me directly, okay? Don't wait until I'm in a different topic. Okay, so 11, 18, 11, 19, 11, 20, and all those things. Now this outcome satisfies event A. Why? Because the first resistor is greater than 10, right? Yes. The first resistor is greater than 10. So this is our event A. So what about event B? I foresee that I won't have enough space. Okay, what is event B again? I can't see it. It's super not helpful. Okay, hold. Okay, let me duplicate this slide. We're just second slide. Oh my God, I'm so slow. Okay, kejap. This. Myself. I like myself, but you have to go first. Okay. So let event A, blah, blah. Okay, let B be the event that the second resistor has a resistance less than 19. So any pair that has the second resistor, oh my God. Okay, so let's write that down. So event B, anyone wants to help me over here? Event B, so second resistor has resistance less than 19. So 18 lah, 9, 18. So next, what's the next?
9, 18.
9, 18, already wrote that down. Next,
10, 18.
10,
10,
18.
18.
Okay. And
11,
18.
okay, 11, 18 and 12, 18. Okay, so this is event B. Okay, event C. Sum of the resistance equal to 28. So here what you have to do is you need to sum the pairs up. For example, this is 30, so this does not satisfy event C. This satisfy event C, so 10, 18 should be inside event C, for example. So this requires a lot of calculation. Let's look at the solution. So the sample space for the experiment is this guy. We already know this. Events A, B, and C are given by. So for event C, we only have 2 outcomes. Okay, so looks like we got this right. Okay, moving on. Do we have any questions with regards to the sample space and events? Is everyone okay with this concept now?
so far,
All
so
good,
good.
Okay, great. If you have questions, you can ask me. So now we're moving on to event relations. Event relations. So previous class, I asked you if you are familiar with Venn diagrams. So Venn diagrams talks a lot about event relations. So this is an example of a Venn diagram. Oh, I have someone in the chat. Let me look at it. Okay, doctor. All right. Thank you for informing me. Okay. All right. So this is a Venn diagram. We're going to talk about that in a bit. So event relations. So we have 3 over here. The first one is union. Second one is intersection. And the third one is complement. So union, as you can see over here, it is everything. If we're talking about event A and event B, it is both. It is both, okay? And if we're talking about intersection, when we're talking about event A and event B, what is the portion that is overlapping between event A and event B? And for complement, anything that is outside of event A. Anything that is outside of event A. Okay? So what is union? The union of 2 events A and B is the event that either A or B or both occur. So it can be either or and also both at the same time. So basically A and B. So you write it like this, A union B. So this is easy to remember because it looks like a U. A union B. It means when the question tells you event A or B, so you have to use union, okay? Event A or B or both. And then when we're talking about intersection, the intersection of 2 events A and B is the event that both A and B occur when the experiment is performed. The key word here is and. Just now it was or. So if I'm asking you, Okay, so I have two students. One is Irie and one is Haziq, right? So I ask Irie and Haziq, have you guys had breakfast? Because you're supposed to be fasting, right? And Irie said, yes. And Haziq said, yes. So this is event A and sorry, this is not a good event because this is outcome. Let me rephrase this example. I need a bigger sample space. Do we have an example later on? Okay, we do. Okay, let's go with that so that I don't mess up the example. Okay, so the intersection of two events A and B is the event that both A and B occur. Okay, so back to the Irie and Haziq example. My event is students who are fasting, right? Student who is fasting. So Irie and Haziq both are fasting. So they intersect in the sense that they are both fasting. So we can say that Irie and Haziq share the same trait, right? I should write it like this. Haziq, oops, salah je. Haziq is fasting. For example, Irie is fasting. Okay, what about the other students in the class? Let me try to remember some names. Fatin, not fasting. Just kidding. This is just an outcome, not fasting. So this is my sample space. So my event is students who are fasting. My event is student who is fasting. So Haziq and Irie is fasting. So we have that. No, this is not right. Event A. We have to have two events. This is not a good example. Just let me stick to the real example that I've prepared. Okay, so complement. The complement of an event A denoted as A superscript C is the set of outcomes that do not belong to A. So as you can see over here, this is an overlap, but if we're talking about A superscript C, we are interested in the part that is not overlapping with A, or you can say this not A. A superscript C means not A. Event A superscript C occurs whenever A does not occur, okay? Okay, so now we have an actual example that I've prepared earlier. Will make more sense. Refer to the earlier example, which was we were talking about the resistors in two boxes, right? So the events A, B, C are given by, we already know this. A is, what was event A about? Event A was the first resistor had to be greater than 10. Let me write that somewhere. A event R1 must be greater than 10, and let B event, the second resistor must be less than 19. Is that right? Must be less than 19, okay. And let's see event B R1 plus R2 equal to 28. All right, so find B union C and A intersect B complement or B superscript C. Let's just call it B complement. Okay, so let's try this one. Find B union C. What does union mean? Union means or, either or. Let me write that, either or. Union is either or, can be either B or either C. Doesn't have to be both at the same time, or it can be both. Okay, so if we are talking about a sample space, this is our sample space, and I have event B over here, and I have event C over here, then I will say this is the union of my events, either or. Okay, so what is B union C? Anyone? How do I write this? B union C. What should be in B union C? Let's try it. If it's wrong, it's okay.
All of the B and C will be included.
Yes, correct. So all of that is in B and also in C will be included in this set. So let's write that 9, 18, 10, 18, blah, 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 9, 19, 10, 18. Okay, so all of that in B and C will be inside B union C because it's either or at the same time both. Okay, do we have?
I have a
Yes.
question.
Yes.
As we can see in B, we got 10, 18, and in C, we also got 10, 18.
Mhm.
So we should write both or just one?
Just one. That's a good question. So, Stasio siapa yang tanya tadi, thank you for the question. So as you can see over here, we have two outcomes that are similar in both B and C. So actually, if we look at this Venn diagram, that 10, 18 would be located over in the middle, right? So you just write it, but you don't have to write it twice. Okay? You don't have to write it twice, just once. So let me make that clear. Just write once. Okay. Oh, habis lagi. Okay, next one. What is A intersect with B complement? Okay, let me duplicate this slide. What is B complement of A intersect with B complement? So B complement is anything that is not B, right? Baguslah Arni. Okay, bagus. Okay, so this is my sample space. As usual, forgive my bad handwriting. Sample space. So we have two events again. We're talking about event A and event B now. Okay, we're assuming that they overlap. But now, let's say this is event A and this is event B. Which portion should I highlight to indicate A intersect with B complement? Which part should I highlight?
one.
The middle one. Sure? So someone is saying the middle one. Is that B complement or not?
No.
No, it's not B complement, right? So A intersect with B complement. This is actually B. It's not B complement. What does B complement tell us? B complement is actually B naught. B naught. Okay, nothing that is B. So the intersect is not correct, but good try. Anyone else wants to try? Is it here?
Just A.
Again, sorry?
Just A.
Just A. But so over here, like this?
Yeah, excluding the overlapping part.
Excluding the overlapping part, correct. So
And then, doctor, if there's a C, if there's like, if there's an intercept between A and C, we have to write C also, right?
if they
There's
sorry?
an intercept of A and C, then we have to write C also, right?
Yes. If we have that event C, yes, we do have to. You have to highlight C as well. If it is outside of B, correct. Okay. Yes.
Ada.
Yes.
Kalau A complement not B kan, dia
Mhm.
bukan sekali dengan kotak luar tu sekali.
Okay, that's a good question. Actually, yes. But now we're talking about A and B only. But that's a good question. Let me get to this point. So this one is A intersect with B complement. Anything that is outside of B and intersects with A is what you should highlight, right? But we haven't answered this question yet. Okay. So to answer the question that your friend asked, so he said, what about the sample space? Shouldn't this be highlighted as well? Actually, since we're just talking about A intersect with B, so this is what I'm focusing. But if I ask you, hey, what is the B complement, right? B complement, we're talking about a sample space, and I'm just concerned about B complement. So B complement would be everything that is outside of B. Okay. But if we're talking between two events, then we focus on these two events only. Okay. That's a good point. Okay, so how do we do this question? Find A intersect with B complement. So what is in this circle? What should be in this circle? What are the numbers? I mean, what is the outcome in this circle that we highlighted? Anyone wants to try? No one wants to try? No one's confident? Oh, this is wrong now. Okay, let me redo this. Okay, this is B, and this is just this guy. So what should be in this circle? Let me write that down. So A intersect with B complement should be, okay, so whatever that is not overlapping with B. So let's see, what are the common factors? Sorry, what are the common outcomes that we can see over here? We have 12, 18. So this one goes out because it overlaps, right? 11, 18, no, 10, 18, 9, 18, no. So the rest of the outcomes in A that is not overlapping with B is inside this subset. So 11, 18. Okay, 11, 19, 11, 20, 11, 21, 12, 19, 12, 20. This is a lot. I'm getting tired. 12, 21. Okay, finally. Okay,
Okay.
so this is your answer. Yep.
11, 18 dia juga.
Oh, okay, sorry. I didn't see it. 11, 18. Thank you. 11, 18 is needs to be removed because it doesn't satisfy. Okay, so any questions about this one? Everyone's okay? All right, moving on. So this is the answer. So B union C is everything that, all the outcomes that belong to either B, C, B or C or both. Oh, macam pendek je. So, B or C or both. This is not right. 9, 19, 10. Oh, I think I made a mistake here. Okay, what about this one? 11, 19, 11, 20. Okay, this one looks right. Okay, let me double check on this one. Okay. Okay, so now we're moving on to mutually exclusive events. After this topic, we're gonna take a 7-minute break or 10 minutes. Okay, so we talked about mutually exclusive events in the previous lecture, and I did not use a Venn diagram, and I realized that it was quite confusing, so I'm going to repeat myself here. So two events A and B are mutually exclusive if they have no outcomes in common. No outcomes in common. More generally, a collection of events A1, A2, etc., A subscript N is said to be mutually exclusive if no two of them have any outcomes in common. So this is a lot of events. We have A, A1, A2, AB, A3, or we can just say A, B, C, D events, right? So if A event and B event do not overlap in any way, so they are mutually exclusive. And I have prepared an example to show that because my previous example was unprepared and usually I mess up. So if two events A are mutually exclusive, then we write it as like this. P, A intersect with B, probability of A intersecting with B is equal to 0. Remember this? Probability. probability of A intersecting with B is equal to 0 because the possibility of them having the same outcome is 0. Okay, so example, again with the resistors. Events A, B, and C are given by this one. Is it possible for events A and B to both occur? Okay, this is my question. Is it possible for events A and B both to occur? Yes or no? And why? Is it possible for A and B to happen at the same time? We just talked about this. Do we have a similar
Yes.
outcome? Yes, right? So
Yes, yes.
event A and event B can happen at the same time if the outcome that the engineer chose, resistors, right, is 11 and 18. So if the engineer took 11 ohm from the first box and 18 ohm from the second box, what happened is he has satisfied event A and also event B because that outcome is in both events. Okay, so how about B and C? Can it happen at the same time? Yes or no?
Yes.
Yes, they have an outcome that is the same. Again, if the engineer chooses 10 ohm from the first box and 18 ohm from the second box, event B and event C is satisfied. What is event B? Event B is, I don't remember. Event B is resistor number 2 less than 19, right? And C is the sum of the resistors must be 28. Okay. Which pair of events is mutually exclusive? Is it A and B? Is it B and C? Or is it A and C? Which event is mutually exclusive here?
A and C.
A
A
and
and
C.
C.
Let's see. We have 10, 18 over here. We don't have 10, 18, 9, 19. We don't have any 9, 19. Yeah, I think so. So which pair of events is mutually exclusive? It is A and C. Okay, someone also answered in the chat. Hakimi said A and C. I think this is correct. Let's see the solution. Whoops. I don't have a solution. So I think you're right. So let's see. Let me look at this properly. 11, 18, 11, 19. A and C. Yep, no overlap. So correct. Yay. Okay, so let's take a break. What time is it? It is 9:43. Let's come back at 9:53. And I'm going to double check on something that I missed out earlier on the example. If you have any questions, you can ask me. Okay, doctor. Okay, Joe. Let me see. Where's my book? Ini pun cukup sangat letter. What's the example just now? Event B and event B union C. Okay. Event B union C. What was the question? Find B union C. Event relation. Betul lah. Okay, welcome back everyone. I hope you are back. 10 minutes already passed. Okay, so let's continue. So previously, I was confused about this answer, but in reality, I read this as A union C. So that's why in my head, I was thinking this should be the answer, but it's B union C. So it is correct. B union C. So B, everything that is in B and everything that is in C. So because they overlap and they are both shaded. So everything in event A and everything in event B should be the outcome. Okay, so no issues here. So that's your answer. Okay, so let's continue with this one already covered. Okay, probabilities. We talked about probabilities last class as well. But of course, that was like an introduction. I'm sure you are still, some of you at least, are still confused about it. So each event in a sample space has a probability of occurring. When we talk about sample space of the resistors, right? Each pair had a possibility of occurring. So the engineer could pick 1118 pair, 1021 pair. So there had to be some probability of occurring. If we repeat that experiment many, many times, we would find out which outcome would be picked the most compared to the outcome that is not picked the most. So that determines your probability. So the expression PA denotes the probability that event A occurs over many, many experiments. PA is the proportion of times that event A would occur in the long run if the experiment were to be repeated over and over again. So the point of this definition, or like this points, is that you can't have probability with just a single experiment. You really can't. You have to do the experiment for a lot of times to understand, so to get the value of probability, okay? So you can't have it like one experiment and you're done, you can't. Okay, so what is the axioms of probability? Let S be the sample space, then the probability of the sample space occurring is always 1. Again, your outcome probability, okay, you have your sample space, you have your outcome number 1, outcome number 2, outcome number 3, etc., outcome N. So all of this has a total probability of 1. Okay, the combination of this will be equal to probability of 1 because they have to add up to 100%, right? So probability of 1, which means that the probability of the sample space to occur is always 1 because, you know, it's the entire outcome. So for any event A is a subset of the sample space. The probability must be between 0 or equal to 0 and less than 1 or equal to 1. It can be equal to 1. Why? Why can it be equal to 1? Because sometimes when you have a population, your subset can be the entire population. Sometimes the events say all of the students are in year 1. So event A is year 1, right? So all of the population, all of the students in this population satisfy event A, therefore the probability is 1. Okay, and sometimes the probability can be 0 in a sense that event B, let the student be in year 2. So no one in this class is year 2, I think. If you're year 2, you don't belong in this class. Okay, so if you are year 2, it doesn't satisfy the population, therefore event B, the probability of event B is 0. Okay, so this is why our probability can be between 0 and 1. If A and B are mutually exclusive events, they don't overlap, like we saw the resistors just now, then P A union B, okay, the probability of A union with B, or the probability of A or B occurring, is equal to the probability of A and the probability of B occurring. So you have to add them up if you want to know what is the union of these two events, even though they are mutually exclusive. Okay, So I want to know I have two events in this sample space. Okay, they are mutually exclusive, no doubt about it, because it already said that. My question is, what is the probability of A or B? It doesn't have to be both, it can be A or B. So A or B is just adding probability of A occurring and the probability of B occurring, okay? So this is an example. The probability that a pin is too short is 0.02. And the probability that a pin is too long is 0.03. So they are mutually exclusive, right? Because a pin cannot be too short, but at the same time, too long. So they are mutually exclusive. Mutually exclusive. Okay. Because, you know, a pin can only be either too short or too long or just okay. So the third axiom says that the probability that the pin is either too short or too long, okay, using this one, is the addition of the probabilities, which is 0.02 plus 0.03 is equal to 0.05. So P, A union of B, even though they are mutually exclusive, is just 0.05. Okay? Any questions about the previous slide? Everyone's okay? Okay? Not okay? Too fast?
So far, okay, Doctor.
So far, okay. So if I'm going too fast, you can let me know, okay? I can repeat myself. Okay, so this is the addition to the axiom. Axiom ni apa? Axiom is like a rule, okay? It's like a rule for math. So for any event A, we're talking about events here. So the complement of event A, the probability of complement A complement is equal to 1 minus PA. Because again, AC is not A. So sample space is 1, right? 1 probability of 1. So I have event A over here. Whatever that is not A is my outcome. And therefore, the probability of A complement is equal to 1 minus whatever the probability of A is. Okay, which is this guy over here. Okay, so if you see this symbol, it means it's an empty set. I don't know how to pronounce this. Let 0 denote an empty set. I shouldn't call it 0. Let me find out what it's called. Let this thing denote the empty set, then P of this thing is equal to 0 because it's an empty set. The probability of an empty set is non-existent. Doesn't happen because when we're talking about probability, there's always something. Okay, what did I want to talk about? Okay, so you've seen this symbol before in AutoCAD. It's not the same thing. AutoCAD, it's diameter. Looks roughly the same. So not that. Okay, not diameter. Okay, if there is a 40% chance of rain, therefore, I want to know what is the chance of it not raining. So it is not rain, right? So if this is event A, I want to know what is the probability of it not raining. Therefore, I'm looking for A complement. Therefore, 1 minus 40% or 0.4 is 0.6. This is equal to complement of A or A complement. So equation 2.2 says that it is impossible for an experiment. Oh, this is addition. First point, second point. Equation 2.2 says that it is impossible for an experiment to have no outcome. This one. Okay, so it is impossible. If you have a probability of 0, it means it is impossible. Okay, let's do this exercise. So I'm going to call out someone to help me. I'm going to give you guys 5 minutes. Try to figure out the sample space. Try to find the subset that correspond to event A and also event B, and then find PA and PB. Of course, 5 minutes. I think you guys can only manage this much. If you can do C, then do it. I'm going to call out someone by random. So please do it. If you can't answer me, then maybe you're not paying attention. Okay, try it. 5 minutes from now. 10:09 p.m. Is it? Yes. Okay. Do we have volunteers or should I pick someone? It's already 5 minutes. Any volunteers? No volunteers? 1, 2, 3, no volunteers. Okay. So I'm going to call out Ahmad Afiq Izzuddin. Are you there?
Yes.
Okay. So what is the sample space over here? Let's do number A. What is the sample space?
Three and four.
What is the definition of sample space? What, from your understanding, what is a sample space?
Sample space is substate or what's the other word?
You can answer me in BM if you're comfortable with that.
Wait, what did you ask? Sample space or subspace?
Sample space.
Sample space. Sample space. Bilangan kejadian yang berlaku dalam satu population.
Okay, correct. So what is your kejadian yang berlaku dalam satu population?
Two crashes, more than two. So meaning 3 and 4.
No, that is event.
Oh yeah, the event.
Okay, try, tak apa.
Oh, you mean the question A below?
Yes, this one.
Okay.
Okay.
Find
Oh,
a
you thought
sample
event A.
space.
All right.
Okay. Find a sample space. 0, 1,
1,
2, 3, 4.
2, 3, 4. Okay, so heads up to those who don't speak Malay. Afiq said sample space is all the outcomes in a population, which is correct. So Afiq, why did you choose 0, 1, 2, 3, 4?
Because all of them has the probability of happening.
Has a probability of?
Happening.
Happening, correct. All of this has a probability of occurring and the total is equal to 1. And again, the total probability of your sample space should be equal to 1 because it is all the outcomes. Okay, thank you, Afiq. Okay, next, B. Who should I call? Can I ask Aida? Who is it?
Can I try?
Who is that? Can you say your name?
Hilman.
Oh, okay, go for it, Hilman. B.
Is the subsets for A 3 and 4, B 1, 2, 3, 4?
B. Oh, sorry. B is 2, 3. Oh, 1. Okay, 1, 2, 3, 4.
1, 2, 3, 4.
Okay, so everyone agrees with Hilman? Thank you, Hilman.
Yeah, I agree.
Agree. So let A event be event that is more than 2 crashes, just 3 and 4, right? So correct. For event B, the system crashes at least once. So it should be 1 or more than, it is equal to 1 or more than 1. So it should be from here to here, 1, 2, 3, 4. Okay, correct. So who wants to try C or should I pick someone?
I want to try. See.
Okay.
So for the PA, the answer is 0.0004.
0.004. Can you tell me how you calculated for this?
0.0004.
Okay. Is this how you did it? P probability 3 and probability 4? Tadi Syahmi kan? Was it Syahmi just now? Oh, 004. Okay, sorry. 004. 00004. Okay. So how did you find out 0.0004? Syahmi, are you still there? It was Syahmi, right?
Actually, my answer is 0.05.
Your answer is 0.05. Okay. Okay, so what was this based off? How did you calculate for this?
I just add 0.04 plus 0.01.
Okay, 0.04, which is probability of 3 occurring, and the probability of 4 crashes occurring. 0.04 plus 0.01. Is this correct, class? Thank you, Shami. Is this correct or not correct? So everyone's confused now? This is not union, we're not talking about union. We're talking about PA, probability of A occurring, and also probability of B occurring. Okay, so let's go back to the rule that we discussed, or like the axiom, and see if we can find any hints from there. So event A, which one was it? Is it axiom? I think there was a statement earlier. Or not yet, I think. Subspace. Okay, let's see if that is correct. Or this one. Okay, not this one, sorry. Axiom P. Okay, let's go with what Shami said. What about probability of B? We'll see the solution in a bit. What's the probability of B occurring? Anyone wants to try, or should I pick someone? It's okay if we get it wrong. We're here to discuss and learn. No one? Okay, how? Can I ask how to tell me what the answer is? Is how there?
Yes, doctor.
Okay.
I think is 0.3 plus 0.05 point
3 plus 0.05
and 0.04 and 0.01.
0.01. So that should give us
0.4.
Yeah. Okay. 0.4, I think. Okay. So let's see the solution. So we completed this exercise. Do I have the solution? So this is S, the sample space is 0, 1, 2, 3, 4 was correct. So all of this that contributes to the total probability of 1 is your sample space. And event A is 3 and 4, and event B is 1, 2, 3, 4, correct? The answer here is to find the probability of A occurring. Notice that A is the event that either 3 crashes happen or 4 crashes happen. Okay, we know this. The event 3 crashes happen and 4 crashes happen are mutually exclusive. Remember, we talked about the axiom of mutually exclusive. So if I wanted to know P3 union with P4, this is 3 crashes or 4 crashes occur, or both occur. So I can use that axiom. The probability of event 3 crashes union with probability of event 4 crashes. I should write it differently. So P3 union 4 crashes, okay, is actually P3 plus P4, even though we did not vision this as a union, right? Because they are mutually exclusive. But they can be a union even though they are mutually exclusive, and that is what the axiom number 3 is for. So I was, this one, this is it? Okay, probability of A union with B. In this case, it is our 3 crashes with 4 crashes is equal to the summation of the probabilities. Okay, this is exactly for mutually exclusive events. You can add them up together. If your question asks you what is the probability of event A occurring and event B occurring, so it's the union. Okay, So any questions about that one? Was that confusing?
So
So I
my answer is correct.
Yes, correct.
Total
Mhm.
for PB,
For
can
P,
I answer like 1 minus 0.6 equal to 0.4 because the event yang zero ni kan tak ada langsung kan. Jadi satu tolak yang tidak langsung dapat segi total yang lain. Boleh kan?
apa? Tak ada halangan. Okay. Yes, you can. I have something in the chat. Actually, Amar yang jawab tadi. Bagus juga. Okay. Thank you, Amar. Okay, so what your friend is saying, for those who don't speak Malay, what your friend is saying, can I do like this? 1 minus B, sorry, what was it? 1 minus complement of B, right? Complement of B will give you probability of B. Yes, okay. So your friend was asking, can I do one sample space minus with the complement of B? Because it is much easier to find out what is the complement of B, because B is actually 4 outcomes of the total sample space, right? This is all B. So if they wanted to use BC is just this guy over here, which is 0.6. Therefore, the probability of B can also be calculated as 1 minus probability of B complement. That's another approach, which is faster and more effective. So you have 2 ways to do this question.
Thank you, Doctor.
Okay, welcome. So everyone okay with this exercise? Okay, moving on. If you have any questions, you can just interrupt me. Oh yeah, I have this example as well. PB 1 minus PB complement 1 minus P0 crashes happen, which is just 1 minus 0.6. This is the other approach. Okay, this is a house approach, and this was Amar / Shahmi. Not sure who was the one asking me that. Okay, thank you very much for the discussion. Okay, moving on to sample spaces with equally likely outcomes. Okay, so when we're talking about population, right? Sorry, let's talk about the resistor again. So when we were talking about the resistor, all the resistors had the chance of being picked, right? And the chance of them being picked was equally likely. There was no probability assigned. Previously, we talked about number of crashes and we had the probability, right? But for the resistors, we did not know the probability. So the engineer could have taken any resistor at random. There was no probability assigned to it. So we can say that for the population of the resistors, all of them have equal chances of being picked. Or I can rephrase this and say all of the resistors have equally likely outcomes. And this is true for when we're talking about population. Okay, for some experiments, a sample space can be constructed in which all the outcomes are equally likely. For and a good example would be rolling a dice, right? When you roll a dice, there is a chance of you getting the value 1, 2, 3, 4, 5, 6. And they are all possible outcomes, and they are all equally likely. So my sample space is 1, 2, 3, 4, 5, 6, and all of them have the same probability if I were to assign. So the probability would be 1 over 6, 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 1 over 6. And the total would be 1 because my sample space should always equal to 1. So a population from which an item is sampled at random can be thought of as sample space with equally likely outcomes. Okay, if a sample space contains n equally likely outcomes, okay, we're talking about outcomes that has, we have n outcomes right now. So we have an event, sorry, we have a sample space, and there is n. N is equal to 6, n equally likely outcomes. The probability of each outcome is 1 over n, 1 over the total population or total sample space outcome. Okay, So another example would be the weights that of my students. So we have 60 students in this class, right? So all of you have, and I want to pick someone at random, and all of you will have a probability of 1/60 if I sampled you guys randomly. For example, we're not talking about events here. I'm just talking about picking you guys at random. I have a sample space. My sample space is you. I just say, okay, I want to pick 2 people at random to do this exercise. So anyone can be my victim, right? Or my volunteer. That's a nice way to put it. Anyone can be my volunteer or my victim. Therefore, everyone is sampled randomly and you guys have equal chances of being picked, which is 1/60, which is not a lot. What is 1/60? Let's see. 1/60 is 0.01, sorry, 0.167. Sorry, 0.0167. So very, very unlikely, but it can happen. There's always a possibility. So always do my exercise in class. Okay, moving on. Sample spaces with equally likely outcomes if A is an event that contains K outcomes. Okay, so just now we talked about sample space. Sample space, the outcome inside is called N, the total number of outcomes, right? When we're talking about events A, then the outcome within event A is called K. So please distinguish between the two. N is for the total sample space. Event is K, inside is K. So if S is a sample space containing N equally likely outcomes, and if A is the event containing K outcomes, then the probability of A occurring is actually K/N. Okay? So remember, we have covered how to determine the number of outcomes in an event and also in a sample space from previous lecture using the product rule, permutation, and combination. So try to relate this topic with the counting rule that we have covered in earlier lecture. Okay, so this is an example. I hope everyone can focus. Sample spaces with equally likely outcomes. Again, specifications are given for the length and the diameter of rods. We're talking about rods here. Here, the table gives you length and also diameter. So you can see over here, it's either too short, okay, which means that the specification is good, and it can either be too long. And for these lengths, the diameter can be too thin, it can be okay or good, and it can be also too thick. So a rod is sampled at random from this population. So I have a box of these rods, which are too thick, too thin, whatever. I pick one, which means that I'm sampling this at random. All of them have equal chances of being picked. We can think of each of the 1,000 rods. So the total number of rods in my box is 1,000. Is this my N or is this my K? Can anyone tell me? Anyone?
N.
It's N. Okay, can you tell me why it should be N and not K?
Because N is the total number.
N is the total number, correct. Or the total number of outcomes in the sample space, correct. So N always refers to your total number of population or sample space, a total outcome, total possible outcomes. Each of the 1,000 outcomes is equally likely. So the number of rods that are too short, okay, let's see if we're talking about rods that are too short. Sorry, I forgot to, the question is over here. A rod is sampled at random from this population. What is the probability that it is too short? Okay, too short, eh? So we are talking about this side. I pick a rod at random. What is the probability that it is too short? So I have to figure that out. So we can assume too short is an event. So the number of rods that are too short that satisfies this table is 10, 3, and 5. So we add them together. So this is K, and 1,000 is your N. So the probability of too short occurring, or the probability of event too short occurring, is 18 over 1000. So 18 over 1000 is 0.0018. So very, very unlikely, but the possibility is there. Okay. What time is it? Okay, it's 10:30. Okay, moving on. So previously we talked about sample space with equal chances, what was it? Sample spaces with equally likely outcomes. Okay, panjang gila. So now we're talking about the addition rule. Okay, so it's a different topic, but over in the same, I would say it's still probability. Okay, specifications are still given. This is the same table that we talked about earlier. If a rod is sampled at random, again, we're talking about sample spaces of equally likely outcomes here. What is the probability that it is either too short or too thick? So now we have two events, too short or too thick. Too short or too thick. Keyword here is or. So we're talking about union here. So event union, the union of event being too short and the union of event too thick. Okay, so too short and too thick is over here. So these are the outcomes if I were to say event A. So I'm going to say too short is event A and too thick is event B. You don't have to write the events. This is just to help with the learning process. So event A is 10, 3, and 5. And event B is 5, 4, and 13. So the union between event A and B is everything within these two events. Okay, we're trying to find the probability here. So everything, all the outcomes within these two events is going to be your K. It's going to be your K. Okay, my question is, what about the overlap? So event A has 5, event B also has 5. Do I put this value twice? Sorry, do I put this outcome twice?
No.
No, we already talked about this, right? If you have an overlap, just put once. You don't have to do it twice. Okay, so the outcomes that overlap with event A and event B, sorry, the outcomes in A and B, sorry, A or B is equal to, I would say 10, 3, 5, 4, and 13. So now I can add these guys together. So 10 plus blah, blah, 35. Therefore, the probability of the rod being too short or too thick is 35 over 1000. Okay. Okay, so now my question is, but wait, why can't we just add P too short and P too thick to get the answer? Okay, remember earlier on we talked about PA plus PB. What was the rule? What was the rule about this one? When we have two events, how do we add them together? It was like this. P union B was PAB. Can I do this for this or for this guy over here? Will I get the same answer? This is union, it's the same. Will I get the same answer?
No,
Why not?
because there's a double in there. You have duplicate in there.
You have the picker in there. What was it? You have the what?
Duplicate.
Oh, duplicate. Who was that?
So,
Zul. Zul, eh?
yeah.
Thank you, Zul. That is correct. I'm impressed. Thank you. So we have a duplicate. So we can't add PA and PB and find out what is the union. You would have a duplicate and that would mess up your calculation. So the axiom that we talked about the axiom that we talked about, let me go back to that, was that if it's mutually exclusive, is A and B in our question mutually exclusive or not? Are they mutually exclusive? No,
No,
they are overlapping. So we cannot use this axiom. We cannot say PA union B is equal to PA plus PB. So that was the catch. It has to be mutually exclusive. Okay, so let me highlight this. Sorry. What's going on? It's not working. Okay. Yellow, mutually exclusive. This is for axiom 3. So how can we apply this axiom in a non-mutual exclusive case? So let's go back. Oops. Okay, so this is what we're dealing with. So my question to you is, just now, I wanted to find out what is PA union B. And the way that we did it was we added all the outcomes, not outcomes, the number of time that it occurs. We added all these together. And this was our K, and we divided by N. So we just added it manually, right? So and then I asked you, why can't we do probability A plus probability B instead? So let me calculate what probability A is. Probability A is, let's do that. PA is equal to, PA is too short, right? 10 plus 3 plus 5. So that is going to be 18 over N. N is 1000. And our PB would be too thick. So that is going to be 5 plus 4 plus 13. Let me just write down the answer. 9 plus 13, 20. 1922, if I'm not mistaken. 22, yeah, 22. So that is going to be 22 over 1000. So if I add these two together, I would get 30, I would get 40. 2 plus, yeah, I would get 40. So PA plus PB would give me 40 over 1000. And it is not the same as the answer that we got doing it manually. This is manually as well, but you get the idea. So you can't add PA and PB just like that if they overlap, because there is that overlap, which means that there is a duplicate somewhere that we have to get rid of. So we should modify the axiom to be like this. For a non-mutual exclusive event, which means that they overlap, therefore, probability of A plus probability of B, you should minus it with the intersect. Which was what we did when we added them manually. We only had one. We didn't add the two duplicates together, right? So we removed one. So remove the intersect from your PA and PB. So note that if A and B are mutually exclusive, then the intersect A intersect with B would be equal to 0. Let me read that again. If A and B are mutually exclusive, okay, they don't overlap anywhere. Therefore, probability of A intersecting with B, right? There's no intersect over here, is 0. So this equation still holds. If this is minus 0, then this is P union B. PA union B is equal to PA plus PB. And this is for mutually exclusive events. I'm ashamed of my handwriting actually. Okay, so that is for your mutually exclusive events. And this is for non-mutual exclusive events. So again, you can just remember this equation. And if you have a mutually exclusive event, then that guy over there would be just 0. So this is easier to remember. And do we have to remember equations for math? Yes, we have to. At least the rules. Okay, the equations or the rules. Okay. So how do we calculate probability for unions? So this is just a recap. So P, probability of A or B or both is equal to PA plus PB, probability of A plus probability of B minus probability of A intersecting with B. However, if event A and B are mutually exclusive, therefore the intersect will be 0 and this equation will be reduced to PA and PB only. Okay. So this is a new topic. I'm going to let everyone have a 5-minute break. If you have any questions, you can ask me now. If not, take your break. Take your break, 5 minutes. 10:44. Come back, okay? So just 15 minutes to go. Okay, so last topic for today, for this class, is conditional probability and independence. Just conditional probability. Let me remove this one first. I don't think we can manage independence today. Okay, conditional probability. So again, using this example that we talked about earlier on, we are sampling a rod, right? It can either be too short, okay, too long, or the diameter can be too thin, okay, or too thick. So we have a population of 1,000 aluminum rods, and that is our sample space number. These 1,000 rods form a sample space where each rod is equally likely to be sampled, and 928 meet the diameter specification. How was that concluded? 928 meets the diameter specification. So, okay, diameter meets the diameter specification means okay. So 900 plus 25 plus 3. So out of the 1,000, we have 928 rods that have a okay diameter. So this is what they are saying. So therefore, if a rod is sampled, the probability of getting a rod with a diameter that is okay is, this is our K, right? Is K over N, 928 over 1,000, which is equal to 0.928. This is fairly straightforward, and we have seen this earlier on. This probability is called the unconditional probability. Because you are finding this probability out of the entire sample space. So again, what is important to know if it's a conditional or unconditional? In this case, this is unconditional. You need to know what is your sample space. It is very, 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 very important to know what is your sample space. What is your N? If you don't know this part, it's going to be hard for you from now on. So you have to know what sample space is, get yourself familiar with it. Okay, so I know my sample space is 1,000 rods, right? And the diameter, okay, if I take a rod and the probability of me getting a rod with a diameter that is okay is 928 out of the 1,000 rods. It is out of the 1,000 rods. Since this probability is based off the entire sample space, this is called the unconditional probability. Okay. So now, what is a conditional probability? So now assume that a rod is sampled, right? So we have taken the rod, okay? We have taken one rod from the 1,000 and we measure its length. Okay, so I have a rod, I measure its length. The length says, it doesn't say anything. I have to measure it using a ruler. So I measure it using a ruler and the specification is okay, right? So now, out of the 1,000, what is the probability, what is the probability that the diameter also meets the specification? So I take a rod, I measure the length, the specification is okay. I want to know what is the probability of me getting a diameter that is also okay. Okay, so out of the 1,000, I picked out a rod that was length okay, right? So it could be any of these rods, whether too thin, okay, or too thick. Now I'm asking you, what is the probability that it has an okay diameter as well? So instead of basing off the probability of the entire sample space, now my sample space is smaller. My sample space is smaller. This is my sample space. I picked out a rod. I know the length is okay, but I don't know what is the probability that the diameter is okay. So now what I have done is I already taken a chunk from the sample space and it is only 900 plus 38 plus 4. This is the sample space that I'm in now. Okay, I took a rod and it overlaps here. Okay, so now from this overlap, or like inside this box, inside this, how do I say this, event, right? What is the probability that the diameter also meets the specification? So I only have 900 over the 942. The total is 942. Let me write that. 942. Okay, so what does conditional probability tells us? It tells us we have reduced the sample space because of an info that we have. We have reduced our sample space because of an info that we have. What was the info that we have? We measured the length, right? We measured the length of our rod, and it says, and the specification was okay. So we immediately reduced the sample space to a smaller portion. And from this smaller portion, I want to know what is the probability of the diameter being okay at the same time the length is okay. Okay, so it is reduced sample space. So how do we write conditional probability? It is P diameter okay. I don't know what this is called, bar, I think. Let me double check on that. I need to know the symbols. Okay, P diameter okay. Let's just call it bar for now. Bar length okay. Now look closely here. It says diameter okay and then length okay. What was the info that I had when I reduced my sample space? Was it length or diameter? Is everyone lost?
Length.
Length, right? So I took a rod, I measured its length. That was the info that I had when my sample space was reduced. From the info that I have, my sample space was reduced. So the info that I have is this, is over at the right side. It's not on the front. So the front part is the diameter, even though this is the info that I have. So this is very important. If you see this type of conditional probability, you have to know that the second part of this is always the first info. This is your limiting. This is the info that is limiting your sample space or reducing your sample space, not the diameter. You should limit your sample space based on your info, which is the second part of this bracket. Okay, sample space. So let's take a look at an example, if we have any. Okay, so conditional probability, find probability of diameter okay or length too long, What is the info that I have here that I have to base off this probability to reduce the sample? Is it the diameter or length? Anyone? Okay, I take out a rod at random. What do I measure first? Diameter or length? Anyone? Come on, guys, let's finish class early. It's just a little bit more.
Length.
Okay, why length? Why did you?
Because
Doctor, is it length because it has the largest number?
Is it length because it has the largest number? No.
Because length is our sample space now.
The length is our sample space now. Okay, other answers? I think that's a partially correct. We try.
It's the limiting factor.
It's the limiting factor, yes. This info is now our limiting factor. Remember, I told you, if you have something, x over here, bar, y over here, this is not y, yx, this guy is your limiting factor. So if I take a rod, I would look at this and say, oh, my limiting factor is yx, whatever that is. Always the second part. If I switch this up, if I say P, length, okay, diameter, thick, my limiting factor is my diameter being thick. The first thing that I look at when I take out my rod is the diameter. That is my info, and that would be my limiting factor that to reduce my sample space. Okay, so let's do length okay diameter sake, because I think that this one is a little bit different than the example earlier. Let's change this. Should I just go with this one? Length too long versus, not versus, that bar diameter okay. So we're changing this. What is the probability of the length being too long and diameter okay? So the limiting factor, or like the info that we have to limit our sample space, is our diameter being okay. So my diameter being okay will be over here only. And then from here, I would know that my sample space is now 9 to 8. Is it? Yeah, 9 to 8. So now I want to know from this sample space that I have already reduced, what is the probability of finding a length that is too long from this sample space? This is now our reduced sample space. So that's that. So that's how you look at it. So reading this correctly is very important. You have to know which one is your limiting factor. Okay, so let's do this one. Let A and B be events where PB, probability of B is not equal to 0. Okay, the conditional probability of A given B, probability of A given B, probability of A given B as in the info, this is our A and B, the conditional probability of A given B is, this is the equation. So probability of A intersect with B over the probability of B. What is the probability of B? Probability of B is length too long over here. What is length too long? I did not do this one yet. Length of too long is 22 plus 25 plus 13. What is that? 15 plus 25, 30, 40. So my sample space is now 40 from the 1000. So this has been reduced significantly. Okay, find the conditional probability given of A given B. So B is our info. Okay, so info is only 40 has rod that is too long. Okay, so we have reduced our sample space to this much. So now we're looking at this chunk only. Okay, so the probability of B is 40 over 1000, and probability of A intersect with B. What is B? A is diameter okay and length too long. So it's just this guy over here. So here, I would say this is B and this is A. So probability of A intersect with B is just 25 over 1000. Okay, so now I think someone will ask me, Doctor, why aren't we using the reduced sample space? Why are we using 1000? Okay, so if I were to put this inside my equation, right? 25 over 1000 over 40 over 1000, it will be gone. And you will end up with 25 over the 40 reduced sample space, which makes sense, right? It's a conditional probability. So the probability of you finding a rod with diameter okay, given the info that your length is too long, is 25 over 40. The end. So we're done with class. Any questions? No questions? So I'll make this lecture note available. Please study. Your quiz is tomorrow. It will cover until conditional probability. Again, for this lecture today, the question is going to be straightforward compared to the lectures that we have covered earlier on. So study well. Don't stress yourself over it. Just do your best, okay? So that is all. Thank you, class.
Thank you, Doctor.
Thank you, Doctor.
Bye-bye. See you. See you in AutoCAD.
Apa bahasa, Doctor?
Thank you, Doctor.
Doctor, will the lab this afternoon will be physical?
Thank you, Doctor.
Welcome.
Yes.
The lab
The lab
will be
this afternoon will be physical or
physical.
Okay, Doctor. Thank you.
Okay, see you. Bye. Stop recording.